Hello everyone, welcome back to our channel. In this video, we are going to learn about one of the most important simplification techniques in digital electronics, that is Karnaugh Map, or we can also call it as the K-map. If you want to learn how to simplify complex Boolean expression without using the long Boolean algebra methods, then this video is for you. So let's get started. First, let us understand what a K-map actually is. A K-map or the Karnaugh map is a graphical method which is used to simplify the Boolean expression or the logical functions. And it is based on the truth table of the logic circuit. The main purpose of the K-map is to help us to minimize the digital circuits easily without going through long and complex Boolean algebra simplifications. Each cell in the K-map represents either a minterm or the max term. In minterm, the dominating value is 1 and in max term, the dominating value is 0. In K-map, we are going to see the grouping of the cells. The proper grouping of cells will help in reducing the number of logic gates in the circuit, reducing the complexity of the circuit, reducing the overall hardware cost and the power consumption of the circuit. Hence, K-map is a simple and optimized visual way to achieve the circuit optimization. These are all the advantages of the K-map. Now, let us see the rules that must be followed strictly while simplifying Boolean expressions using the K-map. These rules help us to ensure that we get the most simplified and accurate expression. So, let's see the rules one by one. The first rule is grouping must be in powers of 2. That means each group should have 1, 2, 4, 8 and so on cells. This depends on the 2 power like 2 power 0, 2 power 1, 2 power 2, 2 power 3 and so on. Like this, the grouping of cells should be in the powers of 2. The second rule is only adjacent cells can be grouped. Means the diagonal grouping is not allowed in the K-map. Only we can able to group the adjacent cells. And the third rule is each group must contain only ones for the SOP or zeros for the POS simplification. This SOP and POS are the two types in the K-map. SOP stands for sum of products and POS stands for product of sum. In SOP, 1 is the dominant value and in POS, 0 is the dominant value. Next, the fourth rule is groups should be as large as possible to get the minimum expression. Means while grouping in the K-map, we can able to group the single cell, double cell or like the 4 cell you can able to group and so on. But always you must concentrate on grouping the maximum number of cells at a time so that it is very easy to simplify the expression. The fifth rule is overlapping is allowed. That means a cell can belong to more than one group if needed. The sixth rule is wrap-around grouping is allowed. That means the leftmost and the rightmost cells or the top and bottom cells are considered adjacent. And we can able to group them together. The seventh rule is every 1 or 0 must be covered at least in one group. Here, 1 is considered in the SOP and 0 is considered in the POS. In SOP, all the 1s in the K-map should be grouped. In POS, all the zeros in the K-map must be grouped. Next, the eighth rule is about the don't care condition. The don't care condition is nothing but the unknown value. In the world of digital electronics, you can't able to expect zeros and ones at all the time. Sometimes the unknown values are come into picture that are called as the don't care. So this rule is belong to that unknown values. The don't care conditions or the unknown values can also be used to form larger groups for further simplifications. Means while doing the grouping of cells in the K-map, if unknown values are present, then you can use them to get the simple expression at the result. Now, let us understand the types of simplification in a K-map. There are mainly two ways of simplifying a Boolean function using a K-map depending on whether we are grouping ones or zeros. These are called SOP and POS forms. Let's understand both the forms separately. First, let us understand SOP. SOP stands for sum of products. In the SOP form, we group all the ones that is logically high outputs in the K-map. Each group represents a product term, meaning an AND operation. Finally, all the product terms that are ORed together, which gives an AND OR circuit. Example, here we considered a three-variable function, that is f of a, b, c, which is equal to summation of 1, 3, 5, 7. So let's move with the POS. POS stands for product of sum. In the POS form, we group all the zeros, that is logically low outputs in the K-map. In the K-map, each group represents a sum term, meaning an OR operation. Finally, all the sum terms are ANDed together based on OR AND circuit. The examples of the POS will look like this. Here we consider two variable function, that is f of a comma b, which is equal to pi of 0 comma 2, which means the values zeros are present. Now let us look at the K-map charts and understand how they are arranged, where each K-map has a number of cells that depend on the number of input variables. The total number of cells is given by the formula 2 power n, where n is the number of variables. Based on the number of variables, we are going to see the different kind of the K-map charts, like 2-variable K-map, 3-variable K-map, 4-variable K-map, and 5-variable K-map. Let's understand each of these one by one. First, let us understand the 2-variable K-map. Here we have the two input variables that are a and b. Since the number of cells in the K-map is given by 2 power n, where n is the number of variables, so here we considered a and b. So our number of variables is 2. So n equals 2, so that the total number of cells will become 2 power 2, so that total number of cells is 4. This means our 2-variable K-map will have 4 cells representing 4 possible combinations of inputs a and b. In the chart, the rows are corresponding to the values of a and the columns corresponding to the values of b, and each cell corresponding to a minterm or the combination of a and b. In a 2-variable K-map, we can make group of single ones when if no adjacent ones are present, and pairs of ones when 2 adjacent cells are present, and a group of 4 ones if all the cells are ones. You must always remember the group size must always be in the power of 2, that is 1, 2 or 4. Now let us understand 3-variable K-map. Here we have the 3 variables a, b and c. So the number of cells equals 2 power 3, which is equal to 8. So we arrange the 8 cells in a 2 cross 4 grid, where row corresponding to a equals to 0 on top and a equals to 1 on bottom. The columns corresponding to the pair BC in a gray code order, which should be arranged as 0, 0, 0, 1, 1, 1 and 1, 0. This order should be in the same manner, where 0, 0 represents B bar C bar, 0, 1 represents B bar C, 1, 1 represents BC and 1, 0 represents B C bar. While grouping the cells in the 3-variable K-map, the group should be of 1 cell, 2 cell, 4 cell or 8 cell. Always we must give more concentration on grouping the maximum number of cells together, such that first we need to check whether it is possible to group all the elements in the K-map. So we are going to get a group of 8 cells. If it is not, then we should move for grouping of 4 cells. If grouping of 4 cells is also not possible, then we must move for grouping 2 cells together. If grouping of 2 cells is also not possible, then finally we must group the individual cells and we must take the result. Now let's move for 4-variable K-map. Now in 4-variable K-map, we have the 4 variables that are A, B, C and D. Since the number of cells in the K-map is 2 power n, for the 4 variables, we get 2 power 4, that is equal to 16 cells. So these 16 cells are arranged in a 4 cross 4 grid. In the chart, now let's look at the row variables. In row, we have A and B, where the rows represent the combination of variables A and B which are arranged in gray code manner. Here we use gray code instead of binary because gray code ensures that only one bit changes between adjacent rows, which is necessary for correct adjacency in K-maps. In row, first we have 0, 0, which is equal to A bar, B bar. In the second row, we have 0, 1, which is equal to A bar, B. In the third row, we have 1, 1, which is equal to A, B. And in the last row, we have 1, 0, which is equal to A, B bar. Now, let us see the column labels. The column represent the combination of variables C and D, which are also arranged in gray code order, which are 0, 0, 0, 1, 1, 1, and 1, 0. Here, 0, 0 represents C bar D bar, 0, 1 represents C bar D, and 1, 1 represents C D, 1, 0 represents C D bar. Again, gray code ensures that every side-by-side column differs by only one bit, keeping adjacency intact. Okay. In this 4x4 K-map, adjacency works in 4 different directions. First one is left to right wraparound, which means the first and last columns are adjacent. Second one is top to bottom wraparound, which means the first and last rows are adjacent to each other. The third one is horizontal adjacency, which means side-by-side cells are adjacent to each other. The last one is vertical adjacency, which means top-bottom cells are adjacent to each other. Because the K-map is a wrapped surface where edges are connected to each other. So, when coming for the group sizes, in a 4-variable K-map, you can form a groups of 1 cell, which is the minimum, or you can group for 2 cells, or you can go for the group of 4 cells or 8 cells. At last, you can group the maximum of 16 cells together. Here also, you must always remember the group size must always be in the powers of 2, such that we can go for the single cell group or pair grouping, that is of 2 cells together, or quad grouping of 4 cells together, or octet grouping of 8 cells together. Finally, entire 16 cells grouping. So it conforms the full map. Now let's move for 5-variable K-map. The 5-variable K-map, which is slightly bigger than 4-variable K-map version, but follows the same basic idea. Here we have 5 input variables that are V, W, X, Y, Z. Since the number of cells in the K-map is 2 power n, for 4 variables, we get 2 power 5, which is equal to 32 cells. These 32 cells are arranged in a 4x8 grid. Let us first look at the row variables. Row are labeled using the variables Y and Z, and they follow gray code order that are 0, 0, 0, 1, 1, 1, and 1, 0. Here also, only one bit changes from one row to the next row. This ensures correct adjacency in the K-map. So, when we observe the column labels, columns are labeled using the 3 variables that are V, W, and X. Here also, these 3 variables are arranged in a gray code manner that are first 0, 0, 0, second 0, 0, 1, third 0, 1, 1, fourth 0, 1, 0, fifth 1, 0, 0, sixth 1, 0, 1, seventh 1, 1, 1, and last 1, 1, 0. This gray sequence ensures that only one bit changes between the adjacent columns, which maintains the proper adjacency for grouping. Inside the every cell, you can see the numbers like 0, 4, 12, 8, 16, up to 22, 30, 26 at the last of the K-map. These numbers represent the minterms of all 5 variables. This ordering ensures that adjacent cells differ by only one variable, which is essential for grouping. In this map, adjacency works in several directions. First one is left to right wraparound, which means first and last columns are adjacent to each other. The second one is top to bottom wraparound, which means first and last rows are adjacent to each other. The third one is horizontal adjacency, which means cell next to each other in the same row, which are adjacent to each other. The last one is vertical adjacency, which means cells above and below are adjacent to each other. This allows us to create many grouping possibilities. Now let us discuss about the group size possibilities in 5-variable K-map. In a 5-variable K-map, the maximum group size is 32 if all the cells contain 1. The valid group sizes in the 5-variable K-map are 1 cell, 2 cell, 4 cell, 8 cell, 16 cell and 32 cells. So, in a 5-variable K-map, 4 cells group appear as a 2 cross 2 blocks. 8 cells group appear as a half of the row or half of the column or wrap around rectangular blocks. And the 16 cells group appear as entire upper half of the map or entire lower half of the map, or left half means 4 columns or the right half means 4 columns in the K-map. Finally, this 5-variable K-map is extremely useful for simplifying the large Boolean expressions where 4-variable K-maps are not enough. By using rows for YZ and columns for VWX, we can visually identify adjacency and create very large groups which leads to minimal expressions. Alright, so this video was completely focused on the theoretical concepts of K-map. We understood what a K-map is, why we use it, and the rules for grouping and how the charts are arranged for 2-variable, 3-variable, 4-variable and even for 5-variable K-maps. These basics are very important before we start solving any problems. In the next video, we are going to take this knowledge forward and solve K-map problems step by step. In the next video, we will learn how to simplify different Boolean functions for different numbers of variables and will practice grouping in real K-map examples. So, if you want to learn how to solve K-map practically, make sure you watch the next video. Thank you for watching and don't forget to subscribe our channel. Let's meet in the next video. Till then, bye.